Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture, except for today, where we will permit ourselves to indulge in a moment of unnecessary detail, all so that we may attempt to answer the question, why is blood red? If you're not interested in a detailed discussion involving quantum mechanics, electrons functioning as waves, atomic orbitals, and molecular orbitals, then I'll tell you the quick short answer. It's a pi to pi star energy transition on the porphyrin ring. But if you'd like to hear about all that stuff, then buckle up. Things are about to get detailed. Now, you may be wondering why I chose this question to go detailed with. And the answer is because that if you were to type the question, why is blood red, into Google, many of the results are misleading or just flat out wrong. To the point that even Google's own generative AI does not give a satisfactory answer. Instead, the answer it gives is blood is red because of hemoglobin, a protein found in red blood cells that carries oxygen throughout the body. Hemoglobin, a red protein that carries oxygen from the lungs to the rest of the body. Hemoglobin contains a protein called heme, which contains iron. When iron reacts to oxygen, it becomes red. Now that answer makes it sound like the iron reacting with oxygen is responsible for the red color. However, in their own generative AI, it goes on to say that blood is red even when oxygen isn't bound to iron. And you'll find more discussion online of people being confused, saying, I thought that iron complexes were green. Why is the one in hemoglobin red? One forum had an incorrect response to this, saying that, when the oxygen comes in and it all binds together, the crystal field splitting is such that the shift in the wavelengths absorbed is such that the iron complex becomes red. So let's talk about what it is that these people are assigning the color to, and then we'll discuss why it's wrong. Transition metals contain d electrons. There are 5 d suborbitals in every shell. If the metal is on its own and there is nothing attached to it, those 5 orbitals are what we call degenerate. They all have exactly the same energy level. However, when ligands bind to a metal center, they do so through a lone pair. They push their lone pair towards the metal, which accepts them. This puts in electron density. If we were to consider an octahedral metal center, the ligands are bound along the x, y, and z axes. So there is an additional electron density coming in along those 3 axes. 2 of the d orbitals lie along those axes. There is the dz squared, which lies along the z-axis, and there is the dx squared minus dy squared, which lies along the xy axis. Because the ligands are putting electron density into those orbitals, it becomes more difficult to put other electrons there. So their energy level goes up. And we now get a gap between the lower energy d orbitals and the higher energy d orbitals. And if light of the correct wavelength were to strike the metal center, then an electron could be promoted from the lower orbital to the higher orbital. Color would be observed. Now, there are a couple of problems of saying that this is the reason for the color of blood. Yes, some iron complexes are red in color. However, the intensity of the color for blood is too great for it to be a D to D transition. Let me show you with a quick calculation. For a healthy human, in 1 liter of blood, there should be approximately 150 grams of hemoglobin. The molar mass of hemoglobin is approximately 65,000 grams per mole. So the concentration of hemoglobin in a healthy human's blood is going to be equal to approximately 0.0023 moles per liter. Each molecule of hemoglobin contains 4 iron atoms. So our concentration of iron is going to be approximately 0.0092 moles per liter. We can now use the Beer-Lambert law to approximate what the absorption of blood would be if the color is due to a D to D transition. The Beer-Lambert law says that the absorption is equal to the molar attenuation coefficient times the concentration times the path length. For spin-allowed D to D transitions, we expect the molar attenuation coefficient to be equal to approximately 100. So if we put in 100 for our attenuation coefficient and 0.0092 for the concentration of iron, and we'll have a 1 centimeter path length, as is standard when recording a UV vis, we find that the absorption is equal to 0.923. We could be generous and we'll round it up to 1. However, that would mean that 10% of all the light going into a sample of blood would come straight out the other side. It would look translucent. You would be able to see through it, which is clearly not the case if you've ever actually looked at blood. And experimentally, we find that the molar attenuation coefficient for blood at about 550 nanometers is approximately 55,000. 2 orders of magnitude greater than what we would expect for a spin-allowed D to D transition. Another problem with this explanation is that if you replace the iron in blood with zinc, which is something that does happen when there is lead poisoning, the color is still red. The reason this is a problem for our D to D energy explanation is that the zinc ion has 10 D electrons. Each orbital can hold 2 electrons. So with 5 orbitals, there is a maximum of 10 electrons allowed. So all of these orbitals are full. Light can come in, but there is nowhere for an electron to move up because all of the upper higher energy orbitals are already full. So zinc complexes are normally colorless because there is no D to D energy transition. But a zinc porphyrin, a zinc-like blood system, is still red. So that's not possible for it to be colored by a D to D energy transition. Furthermore, if you actually take the iron out of these heme groups, these porphyrins that hold it, those molecules are still red. They're still colored. So something else must be going on. This structure here is known as a porphyrin. It has the same general shape and structure as the area in heme, so the part of blood that binds metal centers. If you look around it, you will see that it contains alternating double and single bonds. It is also planar, it is flat. And if you were to add up the number of electrons in that alternating double and single bond system, you will find that there are 18. The rules for aromaticity say that for something to be aromatic, it must have conjugation, so alternating double and single bonds. It must be planar, it must be flat, and it must have 4n plus 2 electrons. If n is 4, 4 times 4 is 16, plus 2, 18, 18 electrons. This is a conjugated pi system. We can even approximate the energy of this system in a couple of ways. First, I will approximate it by using the particle in a box. This is the idea that an electron on the subatomic level, so the quantum mechanical level, can function as a wave. It's not just a fixed particle, it is a wave. And so if we have a box, somewhere where we have infinite energy potential on the outsides and no energy potential in the middle, then our electron can be a wave within this box. It's like when you pluck a string of a musical instrument, it'll vibrate. Same idea here, it is our electron that is vibrating. The only restriction is that we must have nodes, points without movement at each end of the box. For a regular box, we could have a single half wave or a full wave, 1.5, 2, and so on. However, our porphyrin isn't actually a box, it's a ring, which means that we need to take the ends of our box and join it up with itself. This disallows some of those waves we were looking at before. For example, when we just had the half wave coming through, if this was our porphyrin and it came around the other side, it would then be down below as it came past itself. We would have destructive interference. The wave would cancel out, so it's not allowed. If we have a full wave, when it reaches the end and comes back around, it's in phase with itself. So this is fine. So when we have a ring, our particle in a box can only allow whole waves. It can't have any where it's a half. There is also an n equals 0, no nodes state for this system, for an aromatic system. Now, before we jump into porphyrin and talking about doing a calculation there, I want to show you benzene, because it is a much smaller, more simple system where we can actually easily visualize what the atomic and molecular orbitals look like and the numbers of each that there are. For the n equals 0, there's only one option. Everything is in phase. When we go to our first full wave for our particle in a box approximation, we have two options. Our nodes could either sit between carbon atoms, in which case we would have 3 in one phase and 3 in the other, or it could go through carbon atoms, giving us 2 in one phase and 2 in the other. And we're going to say that these are degenerate energy states. And they are higher in energy than our n equals 0, our initial one where everything was in phase. If we go up to having 2, once again, we're going to have options about going through carbon atoms or between carbon atoms. And that will change the number of in-phase and out-of-phase orbitals. This is a higher energy level. And then we've got one more at the top where just everything is out of phase. There are 6 electrons in benzene. Each orbital can hold 2 electrons. So if we start to fill up what we have here, we can put 2 in this lowest where everything was in phase, and then each of the next 2 up that we said were degenerate can hold 2, so there's 4. So those are our 6 electrons. That is where we have electrons for benzene. This top layer is known as the HOMO, the highest occupied molecular orbital. If we go up one more, where we have no electrons currently, that is the LUMO, the lowest unoccupied molecular orbital. And if we had light of the correct wavelength strike benzene, we could move an electron from the HOMO up to the LUMO. It is exactly the same with the porphyrin. We have this ring of 18 electrons. It's aromatic. They're conjugated. There's going to be an n equals 0 at the bottom where everything is in phase. And then we can start going up, saying 1 wavelength, 2 wavelengths, and so on and so forth, generating a very similar system. We know the number of electrons. There are 18. 2 in the bottom, then 4, and 4, and 4, and 4. That's going to be our HOMO. The next level up is our LUMO. I'm now going to show you how to calculate the energy levels of those two orbitals using our particle in a box approximation. The energy of a particle in a box is equal to Planck's constant squared multiplied by the energy state of the particle squared divided by 8 times the mass of the particle multiplied by the length of the box. So for our electron, the mass is going to be equal to the mass of an electron, and the length is going to be equal to the length of our loop, that chain of alternating double and single bonds that goes around the porphyrin. And if we assume that the average carbon-carbon distance is 1.39 angstroms and that the carbon-nitrogen distance is 1.36 angstroms, which are values we can get from X-ray crystallography, then the length of our box is going to be equal to 24.9 angstroms. That n value, we're only going to be allowed even numbers of n because we've linked up the ends of our box. The odd numbers would destructively interfere. Based on what we said before, our HOMO is going to occur when n is equal to 8, which means that our LUMO is going to be when n equals 10. You can then insert the appropriate values to calculate those energy levels. I did this and I found that the energy of the HOMO is 6.22 times 10 to the negative 19 joules, and that the energy of the LUMO is 9.72 times 10 to the negative 19 joules. The difference in energy is 3.5 times 10 to the negative 19 joules. Now all we have to do is calculate what wavelength of light has that amount of energy. This is done from the following formula. The wavelength of light is going to be equal to Planck's constant times the speed of light divided by the energy that we are talking about. And in this case, we find that for a photon to have that amount of energy, it needs to have a wavelength of 568 nanometers. Now wait, you might be saying, why are we calling it a particle in a box? This is clearly a ring, not a box. Well, luckily for us, there is a formula for approximating a particle on a ring, using exactly the same idea of an electron in a ring moving around, and all of those different orbitals. Now in this case, rather than having to know the length of our box, we need to know the radius of our ring. Luckily, there's a very well-known formula for converting a circumference into a radius. And when we do so, we find that the radius is about 390 picometers. If we then do the same calculation as we did before, looking at that transition from the HOMO to the LUMO using the particle on a ring approximation, we get the same answer, that same predicted wavelength of light for this transition. Now let's look at the UV visible spectrum for a porphyrin. Looking at this spectrum, you'll notice that there is indeed a peak approximately where we predicted. But actually there are 4 peaks. And there's also a very large peak off to the side around about 400 nanometers as well. You may be wondering, well, why is there the discrepancy? What's going on? Anytime a scientist wants to calculate an energy level, they need to make some approximations. When we were considering a particle in a box or a particle on a ring, we considered the potential energy inside the box to be 0 and outside of it to be infinity. That is not realistic, so there is a problem with our assumption. We also assume that the box was stationary. Our ring is not moving. There's no vibration or stretching or twisting of the molecule. We know that is not the case. different vibrational states will have different energy states, which will generate different peaks. We also made the assumption that the size of our box would not change, that as we transitioned up and down between energy levels, the size of our ring was always the same. Finally, we said that our ring was 18 electrons traveling around this part of the porphyrin. However, if you look, you'll see that there's actually 2 more double bonds that we excluded from our system. If we were to include those, we would be a 22 electron system. And you can find scientists who consider the porphyrin ring to be a 22 electron system. However, they also assume that the size of the ring is 440 picometers. So it's a larger ring than what we assumed. So having more electrons raises the energy level, but having a larger ring lowers the energy level. And if we were to do the calculation for a particle on a ring, we find we get approximately the same answer again. And by the way, that large peak at about 400 nanometers, that is due to transitions from the HOMO to the LUMO plus one, a higher energy level. But we're not going to go into those calculations. What I hope this analysis has highlighted is how we can apply the scientific method to examine and support or refute an idea. We wanted to think about why blood was red. We found a suggestion online that said the color was due to transitions between the d orbitals of the iron metal center. We were then able to refute this idea. We then had this idea that it could be pi to pi star energy transitions. We made some approximations, and we were able to show that from our calculations, we would expect a peak for a transition between the HOMO and the LUMO in approximately the same place that we see it experimentally. There are also other options we haven't even explored. For example, we could put forward the idea that it is a metal ligand charge transfer, light striking the metal center and moving an electron from it into the porphyrin ring. This type of transfer is the reason why many ruthenium-based compounds are intensely colored. We could attempt to calculate energy levels for the iron 2 going to iron 3 as the electron moves into the ligand, or we could think through some of the points we've already made. The porphyrin is colored even if the iron isn't there. The porphyrin is still red when the iron is changed out for zinc. When oxygen binds to the iron in heme, it oxidizes it from the 2+ to the 3+ state, in which case any metal ligand charge transfer would have the iron going from iron 3 to iron 4 and be at a completely different energy level. So we would expect to see a completely different color. Finally, if it's iron 3+, it's not going to bind oxygen very well. So for these reasons, even without performing a calculation, we can rule out and refute the idea that it is a metal ligand charge transfer that gives rise to the color. Now, heme isn't the only type of blood system we find in nature. There is also a copper-based system. For example, horseshoe crabs have blue blood, and you may be wondering where that blue color comes from. Well, that is a story I'm going to answer right now. It's D to D energy transitions on the copper metal center. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is anything you would like to contribute to this discussion, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.